So, in the previous video, we began with chemical reactions. We are going to be looking at two types of chemical reactions. Basically, the most common types of chemical reactions are going to be precipitation, acid-base, and oxidation reduction. This is going to be another video because I don't want the videos to be too long. Plus, oxidation reduction is a little bit harder, so I'd rather do it by itself. Okay? A precipitation reaction is one in which you have two dissolved substances that react, and one of the products at least is solid. It does not dissolve. Okay? Some people refer to that as double displacement, replacement, whatever. Solubility tells you how much of a particular solute you can dissolve under certain conditions. Of course, if you exceed the solubility, it won't dissolve. Remember when I first got married, my husband says, I'm sick of drinking Coke. My mom used to make tea, always. I forgot I'm in this house, I'm sorry. But his mother died while we were staying. How do you make sweet tea? How much sugar? So I walked up to a neighbor that I knew was a friend of his mother, said, they're probably making tea the same way. And she told me, you add 2 cups of sugar to 2 quarts of water. Wow. I went home thinking, I've dissolved sugar in the lab before. I don't think I can. I mean, I'm used to grams and percentages, but sure enough, I got 2 quarts of water, added the sugar, and stir and stir and stir. It doesn't dissolve. Well, one way you can increase the solubility is heating it up. That's when I learned that you heat up the water and you can dissolve more sugar. And sugar is one of the very few compounds that when it starts cooling off, it does not come out of solution. But solubility tells you the maximum you can dissolve under certain conditions. When you have a large solubility, you say a soluble sugar, you say soluble in water. But if something is not soluble or you add more than the solubility allows you, then that compound will precipitate. Substances that have very low solubility are said to be insoluble, and of course they precipitate out of a reaction. So this is the solubility table that I give my students. Once again, as far as I'm concerned, I say print it out and use it. Use it doing homework, using if you use my worksheets. As far as the exams, check with your instructor. Like I said, I know of one person who makes the students memorize this table. I think it's silly, okay? I don't waste brain memorizing trivia. But basically just saying they're soluble, I say generally because there can be exceptions, but in general when you have group 1 ions, lithium, sodium, potassium, ammonium, they tend to be soluble with no exceptions. They're never insoluble. Nitrates and acetates, they're always soluble because there's no exceptions. But if you start with the halogens, chloride, bromide, iodide, they're usually soluble unless they have silver, that particular mercury, that's a very unusual ion, or lead too. Sulfates, they tend to be soluble, but there's a list of exceptions: strontium, barium, lead, silver, or calcium. That's why I don't understand memorizing this. Now, generally insoluble. If you have hydroxide and sulfides, they're usually insoluble. The exception, or that means they're soluble, obviously when you're using group 1 and ammonium, because we said that they're always soluble. But everything else, if you have a sulfide hydroxide, is insoluble. Sulfides tend to be insoluble, but calcium, strontium, barium happen to be soluble. Hydroxides, we just mentioned them in there. Again, they're usually insoluble. Calcium, strontium, and barium, they're slightly soluble. They don't dissolve a whole lot, but they do dissolve a little bit. Carbonates and phosphates, again, they tend to be insoluble, but we said group 1, ammonium, they're always soluble. So this table, to me, is very, very useful. I have a number of things printed out that I always keep with me when I'm doing things, and I have a periodic table, and the next thing I print out is the solubility table. And when I'm doing problems, I always look it up. Because you say, oh, nitrates are always soluble. Yes. How long before you forget? How long before you start second guessing? What if it's something that's, oh, you can see lead appears many times in the exceptions. So is lead nitrate soluble? Because lead, don't guess. Don't try to remember. If your instructor allows it, use this table. Believe me, it's worth it. So we write a precipitation reaction, potassium iodide. You go to a table. Potassium is group 1, so it's going to be soluble. It's an aqueous solution. Lead nitrate, we say all nitrates are soluble, so it's going to be aqueous. Lead iodide, we say halides are always soluble. Let's go to the halides, except lead. It's insoluble, so we put S. S does not stand for soluble, remember, it stands for solid. Potassium nitrate, this is group 1, this is nitrate, so of course it's soluble, aqueous. Now for the net ionic equation, you have to, I didn't do it in there, but you write 2 potassiums, aqueous, plus 2 iodides, aqueous, plus lead, aqueous, because all these are soluble, plus 2 nitrates, aqueous. That leads to lead iodide that we said is solid, plus 2 potassiums that are aqueous, plus 2 nitrates, aqueous. So now you say, okay, potassium appears in both of them, and nitrate appears in both of them. So what is left? Lead plus 2 aqueous, 2 iodides, aqueous, lead iodide, solid, that is your net ionic. You didn't have to guess that it was going to be solid. You use the solubility table to determine that. You see how easy it is when you have the solubility table? Sodium chloride, silver nitrate, sodium chloride, this is group 1, so you know soluble. Silver nitrate, you know all nitrates are soluble, so it's aqueous. Silver chloride, oh, let's go back to the table. Chlorides, silver is an exception. So silver chloride is going to be solid. Sodium nitrate, group 1 nitrates, so aqueous. And once again, you can do the tall ionic equation. The sodium is going to cancel out, the nitrogen is going to cancel out, and you get here your net ionic equation indicating these are soluble. You realize when you have 2 soluble compounds and then you form a solid that you have to test it with liquid, and when you mix them, then the sodium chloride appears not necessarily as a solid, it may appear just as a cloudiness, depends on the amount, but you do see the precipitate appear. That's the good thing about the net ionic equation. It shows you the evidence of a reaction. We're not going to talk much about evidence of reactions. I usually save that for the lab, but you can ask, what is the point of the net ionic equation? Because it doesn't give you much information. Yes, but it shows you what is the evidence of the reaction in this case, the formation of a precipitate. You're going to see net ionic equations that show you that gases form or something with different color forms. So net ionic equations are very, very useful. Since we're talking about dissolving ionic compounds, we need to mention electrolytes. What's an electrolyte? Everybody knows that when you sweat, you lose electrolytes, and that's why you're replacing drinking Gatorade or Powerade or something like that. There's 2 conditions for an electrolyte. It has to dissolve in water. Most ionic compounds dissolve, but not all. Okay? We saw like silver chloride. That's ionic, but it doesn't dissolve. And this produce ions. So for instance, sugar dissolves in water, but sugar is a covalent compound, it does not break into ions. So you need both conditions. Okay? So substances that do not produce ions when dissolved, they're called non-electrolytes. Let me give you several examples. You have sodium chloride, an aqueous solution. You know that's soluble. it breaks down into sodium ions and chloride ions. So it is dissolved in water, it breaks into ions, so that's an electrolyte. Sugar, C6H12O6, if you dissolve it in water, you end up with an aqueous solution. You don't have ions, so that's a non-electrolyte, even though it dissolves. Silver chloride, if you have silver chloride solid and you add it to water, you still end up with silver chloride solid. It did not dissolve, so that's a non-electrolyte. My favorite, if I want to catch students unaware, sodium chloride solid. And everybody says, sodium chloride is an electrolyte. No, it's the solid. It's not dissolved. You have to dissolve it in water, one, then see if it produces ions. This is not dissolved, so that's a non-electrolyte. I know that sounds tricky, okay? But you have two conditions: dissolve in water, produce ions. You need to meet both. If you're missing one, it doesn't matter if it's the first or the second. If you're missing one, non-electrolyte. Electrolytes can be classified as strong or weak electrolytes, depending how much of the substance dissolves and breaks into ions. For a strong electrolyte, basically all of the substance generates ions. Sodium chloride, it breaks down completely. So that's a strong electrolyte. But for instance, if I have ammonium chloride, you actually, and I'm going to represent it with a double arrow because only fraction breaks down into ammonium and chloride. When only a small fraction dissolves and forms ions, you have a weak electrolyte. Here I'm showing electrolytes got the name because they conduct electricity. When you have ions in solution, they conduct electricity. So you can have three solutions. You plug it in and put a light bulb. When you have a non-electrolyte, like in this case I'm using alcohol, alcohol is not an electrolyte. So there's no light. The light bulb stays off. In this case, they use potassium chloride, but I said use sodium chloride in there. Either one is a strong electrolyte, so you get a very bright light bulb. In this case, they use acetic acid as a weak electrolyte, so you have a weak light. You have a few ions, so you get some light, but it's a weak electrolyte. Only a fraction of the molecules break down to ions, so it produces very little light. Weak electrolyte. The last thing we're going to cover in this chapter are the acid-base reactions. Okay, those are reactions in which a hydrogen ion, a proton, that's another name, because a hydrogen is just a proton and an electron, so if you remove the electron, all you got left with is a proton. When a proton is transferred from one molecule to another, you get an acid-base reaction. So this is going to be very light because we spend a lot of time talking about acids and bases in the second semester. But an acid is a substance that when you dissolve it in water, gives hydronium ions. Basically, the acid releases the proton, but it reacts with water and produces hydronium. Okay? Most instructors will allow you to just say that yields proton. Okay? And this is realistic what actually happens because the proton react with water. Some instructors will accept just protons, some instructors insist you say correctly. I don't see no harm saying correctly. But this is an acid-base reaction because the proton is being transferred from the hydrochloric acid to the water molecule. So that's an acid-base reaction. We talk about hydrogen chloride, that changes name because when you dissolve it in water, it becomes an acid. So protons are lost and gained by the water. You have an acid reaction, the proton reacting with the water to form hydronium ion. That's what we changed the name to. Hydrogen chloride, hydrochloric acid, remember? Strong acids are the ones that dissolve completely. Hydrochloric acid almost 100% of molecules are going to dissolve. So acids that do that, we call them strong acids. Okay. Now, we will explain what makes for a strong acid in the second semester, but we need to cover a whole of material before you're able to understand that. So right now, I said the easiest thing to know, memorize. There's only 1, 2, 3, 4, 5, 6 strong acids. Just memorize them, because if it's not in this group of 6, automatically it's a weak acid. So you have the 3 halogens except for fluorine, and everybody knows nitric, perchloric acid, and sulfuric acid. So really, it's not much of a memory, okay? The advantage again is that then I give you another. How about hydrofluoric acid? Hydrofluoric acid is not in the list, so it's a weak acid. How about nitrous acid? It's a weak acid because it's not in the list of strong acids. Very easy. So there's a whole lot more of weak acids. The only partially dissolved. A large majority remains as dissolved molecules. Only few of them break down. And again, if they're not in the list of strong, that means that they're weak. Easy. So for instance, acidic acid. And notice that every time we have partial dissociation, I represent it with the double-headed arrow. Only about 1% of acidic acid molecules are ionized. Only 1% break. That means 99% stay as acidic acid. It's a very weak acid. That's the acid in vinegar. You put vinegar in your salad, it doesn't burn you. I mean, if you put it in your eyes, it's going to itch. But that's by the extent of it. It's a very, very weak acid. Okay? Now, bases, and there's actually bases that don't really match this definition, but again, I don't want to get into the second semester. We're going to use the simple definition. A base is a substance that when you dissolve it in water, gives hydroxide ions, OH-. So the most common bases are going to be hydroxides, and if you're talking about groups 1 and 2, they are strong bases. Sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, they dissociate completely, so they are strong bases. There you have an example, sodium hydroxide dissociating to sodium and hydroxide. This is a dissociation. This is not an acid-base reaction, because an acid-base reaction, remember, means that a proton is transferred from one molecule to another. There's no proton being transferred in here. This is just sodium hydroxide dissociating. But it makes for a strong base because it dissociates 100%. And like I said, if you want, rather than a list, all of the hydroxides of groups 1 and 2, they're going to be strong bases. Very easy to remember. Now, we have weak bases. Either they don't dissociate completely, or they don't have hydroxide to begin with, like ammonia. Ammonia is a weak base, but it doesn't have any oxygen. How can I release? Well, ammonia reacts with water and forms ammonium ion and hydroxide. This is a partial reaction. Notice a double arrow in there. So it's weak because it's not 100% of the ammonia forming ammonium and hydroxide. But it's a base because it forms hydroxide. That's why we're going to see that there's many definitions of bases, but this takes place by acid-base reaction. This is an acid-base reaction. The one with sodium hydroxide, no. All it did was dissociate. But here, you're having a proton from the water being transferred to the ammonia, so that is an acid-base reaction. Okay. Finally, the reaction between an acid and a base to form a salt and water is called neutralization. Please keep in mind that that doesn't mean that this solution is going to be neutral. We're going to be talking about acidity and pH and all of that. We are not going to cover that again until the second semester. This solution may or may not be neutral. It depends on the salt. Okay? It's called neutralization because the acid neutralizes the base neutralizes the acid, basically. Okay? So you have a base, magnesium hydroxide, an acid, hydrochloric acid. They form salt, magnesium chloride, and water. Once again, if you want extra help, if you have questions, if you want any of my worksheets that will help you a lot to prepare for exams, go to Wisant, the link is in my video description, and make an appointment, and I'll be glad to help you.